All right, welcome back everyone from the weekend. Hopefully nice de-stress. I don't know, what's your guys' homework status in fluids right now? Busy?
We've got a test at the end of this week,
Okay.
so, and homework due today.
I find it easier to have the test the week before fall break, because other people like to have it that way, so making sure I have divided attention. Before we had the exam, we were looking at phase equilibria. If you were on a hypothetical exam, let's say exam 2, that'll be in, 4 or 5 weeks, maybe 6 weeks, I don't know. What would be your starting point equation?
Fugacities are equal.
Not just fugacities, what about, which type?
Partial fugacities.
Partial fugacities. So our starting point would be that the partial fugacity of every species is equivalent across all phases of J. So what our challenge is, this is our governing equation. Our challenge is, how do we estimate the partial fugacity of some species in some phase as a function of temperature, pressure, and composition. Now, if we take this information, we input it into our governing equation for phase equilibrium, we can solve effectively for any single one of these components, right? At what temperature does the system boil? At what pressure does the bubble point occur? At what composition are the two phases at a given temperature and pressure? And this will allow us to design basically any arbitrary separation process that we would like. Now, the challenge here is that different phases more or less have different degrees of complexity in order for us to estimate what the partial fugacity is. So, for our purposes and for most chemical engineering purposes, there are two primary types of phase equilibria that we are interested in. Well, there's a lot of other ones, but the two main ones we'll focus on are vapor-liquid, so I'll call this vapor-liquid equilibrium, VLE, much easier to write that. And 2 is going to be liquid-liquid, LLE. Now we can also have solid liquid, gas liquid, but unfortunately we have significantly less robust ways of approximating those. So these are the two ones that are going to be most commonly used, and are the ones where we have the most theoretical insight into the processes themselves. So based on your previous experience, which of these two is an easier one to tackle?
VLE.
Why is VLE easier?
Because temperature and pressure are constant.
Well, temperature and pressure are going to be constant in liquid-liquid equilibrium.
Oh, okay.
Fugacity of the vapor is easier to estimate.
Fugacity of the vapor is easier, yes. But typically when you do vapor-liquid equilibrium as an undergraduate, you would neglect all the non-idealities in the liquid phase. In liquid-liquid equilibrium, you physically cannot. So now what we're used to seeing is we take the partial fugacity of the liquid equals to the partial fugacity of the vapor. If we assume it's ideal gas plus ideal liquid mixture, now we'll be going over this again continuously, so I'm going to skip over all the assumptions so that we can get to the end goal here. This is our Raoult's law expression that we are so accustomed to seeing, right? If it's an ideal vapor, that means that the pure fluid fugacity is the pressure. The ideal mixture is just the mole fraction weighted by the pressure or the partial pressure. In the liquid phase, the best estimate of the fugacity of a pure liquid is the saturation fugacity, which in this case is the vapor pressure. And then ideal mixing, meaning we just scale it by the mole fraction of the liquid phase. So in this case, vapor-liquid equilibrium with these approximations becomes a simple linear expression for all variables except for temperature. Because the temperature, it's an exponential function for the vapor pressure. However, in the Sandler Thermo book, this is called a non-simple mixture, and we'll talk about that today, hopefully, if I don't go too long-winded. Whereas a liquid-liquid system is what they call a simple mixture. Now, the reason behind this, and we'll illustrate it with the TXY diagram, is that if I have the fugacity of a pure species at a given temperature and pressure, which phase must it be in, right? It can only be in one phase at a given temperature and pressure. So if we were to rewrite these here with a more robust method, so let's write right, this is what we would call the sort of the phi gamma approach to solving vapor-liquid equilibrium. We'll be talking about it. This is the Lewis-Randall rule. So we have the fugacity of pure vapor multiplied by its mole fraction is the partial fugacity. In this case here, we have the fugacity of the pure liquid multiplied by an activity coefficient, which contains all of the excess Gibbs information, times by the mole fraction. This is the fugacity, partial fugacity of the liquid, partial fugacity of the vapor. Well, notice that here, at a given temperature and pressure, we're saying that we can estimate the pure fugacity of the liquid. Or at the same temperature and pressure, we can also estimate the fugacity of the vapor. The fluid cannot be in both phases at the same time. That's why we call this a non-simple mixture, because our concept of how to solve this problem from thermodynamics actually breaks down. So we have to do empiricism to resolve this issue here. Whereas in a liquid-liquid system, so this is vapor-liquid equilibrium. In liquid-liquid equilibrium, we can write basically this expression twice. So we have the mole fraction of species I in phase 1 times the activity coefficient of species I in phase 1. In this case, we call it phase 1 and phase 2 because they're both liquids. Multiplied by the fugacity of that liquid at some temperature and pressure. Now we go to the other phase, mole fraction of component 1 in phase 2, activity coefficient of component 1 in phase 2, and the fugacity of that liquid at the temperature and pressure again. This is simplified because these two cancel out. So in this order, if this to be a liquid-liquid system, it's most likely going to be in liquid state. So our liquid-liquid equilibrium expression is actually far simpler than our vapor-liquid expression. So why on earth does undergraduate engineering hardly ever cover liquid-liquid equilibrium?
Because I don't want to touch. Oh, never mind.
What do you guys think? Why is it always vapor-liquid and never liquid-liquid? I mean, distillation, yes, is a very, very important unit op.
The coefficient is really hard to estimate, especially at high pressure.
Exactly. Activity coefficients, even the simplest activity coefficient models are nonlinear exponential functions. Activity coefficients are hard to estimate, they're hard to conceptually understand, they are hard to measure. So it's much easier just to focus on flash separations and Raoult's law. But from a thermodynamic fundamental perspective, this is what they call simple mixture. Vapor-liquid equilibrium is a non-simple mixture. Another non-simple mixture would be gas-liquid equilibrium, solid-liquid equilibrium. Those are all non-simple systems, where effectively you are trying to estimate the properties of a fluid that don't exist. And we'll demonstrate, hopefully today, why that's the case. But very briefly, I'd like to first go over how we get activity coefficients before we jump into vapor-liquid equilibrium. So we're going to go through our quote-unquote simple systems. They're simple conceptually. They are non-simple practically, because you have to use a nonlinear solver, which means it's pretty hard to ask liquid-liquid equilibrium questions on an exam. So what we do for activity coefficients the number one most popular way to handle non-idealities in the liquid phase is we just measure data. That's it. We measure data, we assume a model, we fit the model to the data. If the model is reasonable, then we only need a few data points, and then we can come up with a continuum model to estimate it. There are a few predictive activity coefficient models. The most popular among the predictive models that are used most commonly are going to be Flory-Huggins theory, and another one that's popular, it's predictive, but it's actually built on correlations, is the UNIFAC model. So I don't know who recalls their senior design project, for those who are chemical engineers, and you go into Aspen, and they say, what model do you want to use? Do you want to use the Wilson model? Do you want to use NRTL? Do you want to use Flory-Huggins? Do you want to use UNIFAC? UNIFAC is probably the one you wanted to use most often. It's one of the most robust. Now with experimental data and fitting, now this fits us into a number of molecules. The Wilson model, the Van Laar, NRTL, UNIQUAC. Now, the foundation of these varies from 100% empirical, a polynomial fit, to a framework where they just need a few parameters to optimize and tune the model. Right? So it spreads the whole gamut. But I know when I was a student and I was doing my senior design project in Aspen, I felt very unprepared with activity coefficient model estimates. I don't know, was that a shared sentiment, or am I just the one who's a really bad student as an undergraduate? Okay, so there's at least one other person who agrees with me. So let's talk about the simplest one. This is going to be the, what do we call it here? It is the one constant Margules. Sorry, let's add this to the list. One constant activity coefficient model. This is the simplest one, but it's really great in highlighting how you do this process. So the objective here is that if we can measure the excess Gibbs energy as a function of the composition. This could be a multi-component system, but for the purpose of visualization, let's keep it as a two-component system. Does anyone know how we experimentally measure excess Gibbs free energy? Let's start off with a simple one. How do we experimentally measure excess enthalpy? What experimental technique do we use to measure that?
Thermometry?
Say it one more time.
Thermometry?
Very close to calorimetry. Right, so calorimetry, what you do is you have a little container with a little glass ambule on the inside. On the outside, you have some fluid A. On the inside, you have some fluid B. You crack it, release the two, measure how much heat goes in or out. And that's a calorimeter. That'll measure excess enthalpy. How do we measure excess Gibbs? There is no Gibbsometer that we can put it into. But we have to do this because the entire foundation of all liquid phase properties are benchmarked to experimental excess Gibbs data. Has any of your instructors ever previously talked about this? Okay, I was confused too. So, let me erase that a little bit there so I can. How they do this, and it is an extremely unsatisfying answer, unfortunately. The answer is vapor-liquid equilibrium. This chart here is going to be drawn at a constant temperature and pressure, otherwise you would be varying two variables at the same time. Now typically if you look up thermodynamic data, they'll have multiple lines as a function of temperature or pressure, whatever the interest of the fluid system is. In a vapor-liquid equilibrium system, you'll have a temperature pressure, you'll have a mole fraction and composition of the vapor phase, you'll have a composition of the liquid phase. You will compare this to what the ideal system would calculate and predict. And then you basically just tweak the Gibbs until the deviation between ideal behavior and the real fluid behavior is resolved by the excess Gibbs. This is an excellent way to get access to excess Gibbs. Now, it's not completely unbiased. Typically what happens is most researchers will assume that the vapor phase is ideal and that all of the non-ideality comes from the liquid phase. If not, you'll assume that the fugacities of the vapor follow an equation of state, and then you'll use the excess Gibbs plus what's here, plus what's there, to sort of resolve the whole issue. So it's not completely unbiased. You have to do a little bit of modeling assumptions to actually get the excess Gibbs to plot to even fit an activity coefficient model. But this is one of the reasons why we have really good activity coefficient models for systems that are easy to get into vapor-liquid equilibrium. Now, systems that are very challenging to get into vapor-liquid equilibrium, polymers, heavy hydrocarbons, solids, right? These are much harder to do because we don't have access to this nice, convenient, experimental way of getting the data. So instead, we have to do the more complicated liquid-liquid type separation processes to get access to the excess Gibbs information. So it makes it a little bit more challenging, so it's not as trivial to do, whereas vapor-liquid equilibrium is nice because the separation step is easier. So what happens in activity coefficient modeling for empirical systems? What we will do is we will fit, for this case, the one constant Margules, we will fit the excess Gibbs using a simple polynomial expression. Some coefficient, that's the one constant, multiplied by x1, x2. Now this functional form is adopted such that if the composition of any of these is pure, the excess Gibbs goes to 0, which is what theoretically should happen. Now the activity coefficient is defined based on the excess Gibbs. So the activity coefficient of species I is simply equal to, well, scaled a little bit, to the partial excess Gibbs, which is equal to taking the total excess Gibbs and taking the partial derivative with respect to the change in composition. But you'll notice one problem. This is in terms of mole fractions. This is in terms of the total number of moles. So the math is a little bit more tedious than may immediately seem. But once you see an example once, it's not too bad. So let's work through that math. Partial excess Gibbs of species I. Sorry, let's do it species 1. We have to substitute in our expression here, so we have n times, n times a times n1 over n1 plus n2 times by n2 over n1 plus n2. Make sense? I just substituted n's for a number of moles for the mole fraction. This is the total number of moles here. This cancels out with one of these ones down there. So far, so good. Here we have to use the product rule or the quotient rule. I don't know about you, but I can never remember the quotient rule. So I just do the product rule, but in this case, the exponent is -1. So in this case here, we have derivative of the first times the second. So in this case, it's n2 over n1 plus n2. Plus the first times the derivative of the second. So it'll actually end up being minus n1, 2 squared. Goes out. Now bear in mind, this is the absolute simplest activity coefficient model that we've come up with. All right, so this is equal to here. This is just equal to the mole fraction of component 2, right? Number of moles divided by the total. So this is this one here. This N1 divided by the total number of moles. This N2 divided by the total number of moles is equal to X1, X2. So then lastly, we're almost there. And there we have it. The activity coefficient model for the one constant Margules, sorry, let me add on the end here, is equal to RT, activity coefficient of species 1. And likewise, we can do exactly the same thing, but for component 2, everything is just mirrored. X1 squared. The simplest activity coefficient model. Let's just go back over here real quick. So if we were to plot these out, we can discuss a little bit of the properties and characteristics. In this case here, I have drawn positive excess Gibbs. Does that mean that these two fluids like each other or don't like each other? They don't like each other. That's usually the default. Which means that the pure fluids are happy. As soon as you take a pure fluid and you put it into a mixture of the other one, it should be the most unhappy. The most average happiness should come at a 50-50 mixture. So if we were to plot out, let's see, what do I plot here? I do the activity coefficient as a function of the mole fraction, and this here is actually going to be 1. If we look at, so as we go from 0, x1 to 100% 1, it'll be very unhappy, and then it will go back to being 1. Activity coefficient of 1 means ideal mixture. So this would be activity coefficient of 1. And in a perfect mirror image, this is activity coefficient of species 2. So if we were to look at the vapor-liquid equilibrium, the partial fugacity of the liquid phase is going to be equal to the mole fraction, activity coefficient, times by the pure species fugacity at temperature and pressure. So let's say, for example, we're looking at species 1. If we have a dilute mixture of species 1 into species 2, that means that we will have an activity coefficient that is a large deviation from 1. What will happen is that will raise the fugacity of that species in the liquid phase, meaning it wants to get out. It wants to volatilize, it wants to go into the vapor phase. So you will not have an ideal system because the fluid mixture is such that component 1 really doesn't want to be in that phase. Does that kind of make conceptual sense? As you increase the amount of species 1, it gets happier and happier and happier until it reaches the point where it doesn't even realize that species 2 is in there, and then species 1 by itself behaves as an ideal system. Now in the case of liquid-liquid equilibrium, how we would solve this is we would have effectively these two. And into this expression, we would substitute our activity coefficient model. Now, by far the largest challenge of liquid-liquid equilibrium is keeping track of the coefficients. Because based on this expression, we're looking at here, let's say, sorry, this would be, I should say this is, let's put ones here because we won't be able to use the same nomenclature. This would be activity coefficient of species 1 is dependent on the composition of species 2, which in this case here is 1 minus the composition of species 1 in phase 1 squared. This one here would be a function of the composition 1 minus x 1 in phase 2 squared. So in the case of liquid-liquid equilibrium, we have all of these variables at the same time. x1 of phase 1, x1 of phase 2, x2 of phase 1, x2 of phase 2. So it just gets a little bit tedious with the nomenclature. But as long as you can be consistent, it's really just algebraic substitution and solving one nonlinear expression. Sorry, two. You have this expression here for component 1, and you have the same expression for component 2. But you have to get it all into a system of 2 equations with 2 unknowns. But I'll allow you to all do that in the homework expressions. Now, stepping up in complexity, I will not go over much detail on how these are derived, but the procedure is exactly the same. Instead of using this very simple polynomial to fit the excess data, if we use a Redlich-Kister polynomial, now this form here is we fit excess Gibbs data using a polynomial of this form. This is a Redlich-Kister polynomial. So if we say that B equals C equals D equals 0, that gives us the one constant Margules. If we say that A and B are not equal to 0, that gives us what we call the two constant Margules. These are 100% empirical. So I'll write out the activity coefficient model. Oops. Just notice on my notes I have cubed here but squared there. I think it's cubed. Then I might have a mistake on my notes with the coefficients there. And I'll write out one last one that's pretty common that you'll use a lot in the homework. If you use a different polynomial to fit the data of a slightly different form, we can get the Van Laar equations. And these ones actually work pretty well. Okay. So with liquid-liquid equilibrium, effectively, all we do, set the partial fugacities equal, The only real complexity in the partial fugacity expressions is the activity coefficient models. So from there, it's just simply solving a system of nonlinear equations for the composition of x1 and x2 in phase 1 and phase 2. Now the general equations that you're going to be using are your two fugacity relationships, one for component 1, one for component 2, and then material balances saying that x1 plus x2 in phase 1 is equal to 1, x1 plus x2 in phase 2 is equal to 1. So those are your 4 equations and your 4 unknowns, and you can solve the system. So it's just algebra at that point. That is a simple system. Now let's talk about vapor-liquid equilibrium as a non-simple mixture. Now there are 2 approaches to solving vapor-liquid equilibrium. So in this case, our starting point, the partial fugacity of species I in the liquid phase is equal to partial fugacity of species I in the vapor phase. If we have 10 components, that means we have 10 of these expressions. If we have my comment. How many components are in a group? It's effectively an infinite number of components. It's really an uncountable. But in terms of pseudo components, how do we lump them? You're probably lumping them on the order of maybe 100 different components. Everything below about C6, C7, you can actually directly model. You can measure it, you can know the compositions. There's few enough isomers that you can handle it. Then once you get to about C7, you keep all the C7s as one pseudocomponent, all the C8s as a pseudocomponent, all the C9s as a pseudocomponent. Until you get to maybe about C15, C20, then you start lumping maybe C20 to 30 as a component, 40 to 60 as a component, 60 to 100 as a component, right? And those little cuts get bigger and bigger and bigger. So the reason why equations of state were developed for oil and gas is because computers were becoming more powerful. We wanted to have an equation of state method that we could have an iterative computer-designed optimization procedure to better improve operations of refineries, oil and gas reservoirs, and everything. And with an equation of state, right, as long as the computer could handle the algorithm, it could grind away and grind away and grind away until it found a solution. But as a human, there is no way that I could guess and check 100 pseudo-components to make sure what the vapor-liquid equilibrium was. Right, so that was the foundational development of that procedure. So if you have a good equation of state, we can directly just calculate the partial fugacities from an equation of state. Now the Sandler book refers to this as the phi or phi method, however you want to say this. This is the fugacity coefficient. So in this case here, what we're doing is we are writing the partial fugacity of the liquid, which is a function of temperature, pressure, and composition. We will write it in this form. And we will get this information from an equation of state. Now this is kind of cyclic logic, as all things that we're learning about in thermo. The partial fugacity coefficient is just defined as the partial fugacity divided by sort of the ideal mixing fugacity. But what it allows us to do is that means that this value of the partial fugacity coefficient will vary around 1. So this is all just convenience substitutions, right? You could directly calculate the partial fugacity, partial molar fugacity, partial fugacity with an equation of state. But in this case, they call it the phi method because it's nicer just to see things that are around 1. So regardless of the temperature and pressure, your value here will be like 0.5 to 1.5 to 2. Right? It's not going to vary too much. Whereas with the fugacity, it could go all the way from 0 to 10,000 psi. So it's just a nice, convenient way to unpack it. And then we use almost exactly the same expression for the fugacity of the vapor phase, temperature, pressure, In this case, I'll write Y for mole fraction of the vapor phase, Y P partial fugacity coefficient in the vapor phase. And this, of course, contains all the temperature, pressure, and composition information. If you have an equation of state, and we talked about this, we'll go over it again throughout the, maybe today, maybe not, but basically, we've already provided expressions for how to calculate the fugacity of a fluid using an equation of state with mixing rules. Non-trivial, but it can be done. This works if you have a good equation of state, or if your system is relatively simple. If we were to look at, let's say, the simplest equation of state, the van der Waals equation of state, vapors have two distinct advantages over liquids in terms of their simplicity. One, the density is very low, so that any inaccuracies in your excluded volume are relatively insignificant, because the molecules have a low probability of finding each other anyway. And the density is very low, which means that you have very few molecules that are near enough to feel each other's presence. In a liquid, the opposite is true. The excluded volume is a significant contributor to liquid property behavior, and you have a tremendous number of pair interactions that contribute to the total energy of the system. So both of those two effects make it so that estimating properties accurately in the liquid phase is very challenging. So in many cases, this is just insufficient, which inspires the most common method, the gamma phi method, for low pressure vapor liquid equilibrium. And in this case here, we will still use, for the vapor phase, the equation of state approach, because again, equations of state are actually pretty good for the vapor phase. So in the case, we'll write it as mole fraction, system pressure, partial fugacity coefficient. However, for the liquid phase, we will write as such here. Actually, let me rewrite this slightly different way, sorry. We'll do so instead, we're actually just the saturation pressure multiplied by the activity fugacity coefficient will just equal to the pure fluid fugacity. So this way here we're borrowing as much as we can from sort of the Raoult's law type expression. So I do have the equation here for how we calculate the fugacity coefficient from an equation of state, but I'm not going to write it down again. Just note that it has this big form, so natural log of this is equal to 1 over RT well, I guess I'll just write the whole thing out. I'm halfway there. The challenge here is in what they call the mixing rules. How do you estimate what the pressure is as a change in the composition? Okay. Now let's go into non-simple mixtures. I already introduced it, so let's go straight into what a solution of one of these vapor-liquid equilibrium expressions would go like. So we're going to look at a TXY diagram. Has everyone seen who has not ever seen a TXY diagram or a PXY diagram before? Everyone's seen this type of phase diagram. Good. In this case here, this is for a benzene toluene mixture. Should this be close to ideal or not? It should be very close to ideal. So the convention, there's two conventions here. My personal convention is when I draw TXY or PXY, whatever phase diagrams, I always put Z on the axis here. A lot of times figures will just put X, but I like to put Z because it's the total composition. Now the convention that is followed for simple systems, when it gets complicated, it gets a little bit harder. But you typically will always put the most volatile species on the x-axis. That's the convention, just so that all TXY diagrams and all PXY diagrams look similar. So you can just focus on the differences. So most volatile species on the x-axis. Now what this allows us to do is if we have a mixture of benzene and toluene, right? So benzene is just, I think everyone knows what benzene is. Toluene is benzene, but with a methyl group attached to it. Which of these two has a higher boiling point? Toluene. Well, I told you because benzene is the most volatile. Which means that in the TXY diagram, what we're doing is we're plotting T and then effectively XY down here. So at very high temperatures, regardless of the composition, what phase should I be in? They should all be vapor. At very low temperatures, what phase should I be in? Should be liquid. So that means on this line right here, this is where the mole fraction of benzene is pure. On this line over here, the mole fraction of toluene is pure. At some point on this line, my pure benzene will have its saturation temperature, or its boiling point. Should I draw that up here, or should I draw it down here?
Lower than toluene.
It has to be lower than toluene because it's the more volatile. So in this case, benzene's boiling point, I believe, is about 80. Do I have it right here? Yeah, it's approximately 80. I don't think it's exactly, but about 80. Right, this is the vapor-liquid transition for pure benzene. Note that it is a single point. Now for toluene, it's higher. It's about 110 degrees C. This is where toluene boils. So what we'll be deriving is equations to solve for these two lines. About that shape. What do we call this line here? This is the dew curve. And this line here is the bubble curve. So if I were at, let's say, a composition here, I would start off as pure liquid. I would heat that liquid up. It would stay liquid until I reached the bubble point of that particular composition. At which point I would, let's see, I think I have a different colored marker. I would start to phase separate. Now, this is sort of the trick that I force myself to remember on how to do phase diagrams. Think back to graphical solutions to mathematical systems of equations. How do I solve for phase equilibrium, constant temperature, constant pressure, linearly or graphically on this plot here? So this is all at a constant pressure, right? Constant pressure, composition, and temperature. How do I solve all those?
Well, first draw a constant temperature. That's the easiest.
So draw a constant temperature is exactly right. So I draw a constant temperature, and you'll note that I have two solutions to this equation. Where the temperature line intersects my bubble curve, that corresponds to the mole fraction in the liquid phase of benzene. Where my constant temperature line intersects with my dew curve, that provides the mole fraction of that phase in the vapor, mole fraction of benzene in the vapor phase. So, as I continue to heat this system, I will be in the two-phase region until I get to the point where almost everything is volatilized. Then I will be at the dew point of that mixture, in which case here, this will correspond still to the mole fraction of benzene in the vapor phase, and where it intersects the bubble curve will correspond to the mole fraction of benzene in the liquid phase. Now you'll note that this here, like I write, is always Z, the total composition. But in the case of a pure liquid system, the total composition should be equal to the liquid composition. And that's exactly the case all the way going up to the bubble point. Once I reach the bubble point, I create a second vapor phase. That composition of those two phases changes as I go through the two-phase region until I reach the dew curve, in which case my vapor phase is equal to my total composition of the system. So when I'm in the two-phase region, this is something that's always a little bit counterintuitive. At a given temperature and pressure, changing the total composition doesn't change the composition of the two phases. This is something that's always a little bit kind of counterintuitive. So let's say hypothetically, I don't have a third color, but I wish I did. Let's go back to black then. If we were at this temperature, let's just say this is, I don't know, 99 degrees Celsius, okay? I have a mixture of benzene and toluene at 99 degrees. So that means that the composition of my two phases are those two dots, irrespective of what the total mixture composition is. That means that I can be in vapor-liquid equilibrium at any total Z composition within that window. The only difference is, where do I draw my intersection of the total composition with the temperature, with the pressure? So if I were all the way over here, and I had a lot of benzene, then it would make sense that the limit of my two-phase region would be the dew point, because benzene really wants to be out into the vapor phase. If I had a lot of toluene in the system, then the envelope would be limited by the position of the bubble point. So then this brings us to what they call the lever rule. We need a material balance to tell us how much of each phase. Thermodynamics will tell us the composition, but a material balance tells us how much of each phase. So in the case, this is how I do it, and this is, again, I have juvenile ways of thinking about this, but I think of it as a tug of war between the two phases, right? It's the dew curve versus the bubble curve. Whichever side has more molecules wins the tug of war. I never remember the equation, so if I need to look it up, I'll just look it up. So on the bubble point, the total composition is pulled all the way over to the liquid phase, meaning it's almost 100% liquid. In the case of the dew curve, almost all the molecules are vapor, so the tug of war pulls the total composition over there. But in the case, let's say, of this one here, is it mostly liquid or mostly vapor?
Mostly liquid.
Because the tug of war, the liquids are winning. And this one here, mostly vapor. That's my rudimentary way. But this is something that's a little bit counterintuitive, particularly when we start working with a little bit more complicated and non-intuitive phase equilibrium, like liquid-liquid separations. Right? Temperature and pressure defines the phase composition and number of phases that you have in the system. Material balances tell you how much of each phase. So we need a mass balance in addition to thermodynamics to solve these problems. Okay, last point before we depart for the day. Let's choose this position here, 99 degrees Celsius. What phase of matter is pure toluene in? Liquid. So toluene at 99 degrees C is a liquid. However, in order for us to do the phase equilibrium, we need to be able to estimate the partial fugacity of toluene in the vapor phase of a fluid that does not exist. We need, in order to calculate our partial fugacities, we need to know, oops, not the partial, we need to know what toluene vapor's properties are at 99 degrees C. This is what makes it a non-simple mixture. Conversely, at 99, benzene wants to be in a vapor, but in order to estimate the fugacity of benzene in the liquid, we have to estimate the properties of a fluid that doesn't exist. And this is why, I think I erased it. Oh yes, this is the most important note then that I took on the board to solve this issue. If we assume it is low pressure, what that means is that we can approximate the partial fugacity of a liquid that doesn't exist as about the pressure of a saturated liquid of the saturated vapor. Right, so what we're doing here is that everything from vapor-liquid equilibrium onwards is now empiricism and heuristics, but it works pretty well. So what we do and how we resolve this issue is that we approximate the properties of a fluid that don't really exist, but that behave kind of near to the fluid that does exist. So in the case of going, I'm running a little bit over on time, as per usual. So in the case of a hypothetical liquid, and this would be the benzene scenario, we approximate the fugacity of the pure liquid as what the saturated vapor would be under those circumstances. And then for a we use an equation of state, we'll use correlations, or we'll just say it's Raoult's law because it's a low pressure vapor liquid equilibrium. The vapor phase should behave mostly ideally. But please do note that from this point onwards, these are just tools and strategies. So most thermodynamics from this point onwards are just optimized parameters that fit to specific data. But once you have that, then you can use the power, basically, of numerical methods to solve more and more complicated systems. So the concern here is in choosing a model that best represents the physics of the process, but maybe doesn't have all of the exact detailed information for every single parameter, in which case we'll just fit it to real data. If we do that enough times, we can develop correlations, and then we can rely on those correlations to be semi-predictive. And that's exactly what the unifact model is. It's done that very well. All right. So now on the homework, we'll actually be solving real phase equilibrium problems. Have a good week.